So this is section 8.8. We'll be talking about improper integrals. Everything we've done so far has been what's called a proper integral, definite or indefinite. Okay, so first let's talk about what an improper integral is. Improper integrals occur when the function being integrated has an infinite discontinuity over the region being integrated. Or the way we would write this is limit as x goes to c of whatever our integrand is, the function that's our integrand, is going to be equal to either plus or minus infinity. And we're assuming then we're going to integrate this thing from a to b, and c is on the closed interval a to b. And it could be either a or b. Now, these sort of things usually occur when the denominator equals 0. There are a few other cases we're going to talk about here in just a bit. But this is the most common case that happens. All right. So let's take a look at an example. We're integrating from 0 to 1 of dx over 3x minus 2. Now, at first blush, this looks all right because we could come in and rewrite this thing as the integral from 0 to 1 of 3x minus 2 to negative 1 dx. Okay, we're going to use a u sub as 3x minus 2, which will make du 3. So essentially what I'm going to end up with here then is a integral from 0 to 1 of du, or 1/3 du times u, which is the natural log of 3x minus 2, evaluated at 0 and 1, so it would be the natural log of 1 minus the natural log of negative 2. This is 0. This doesn't exist. Okay, but what happens here is we've got something else. Anytime you've got this down here, you need to worry about when it's equals to 0. So you set your denominator equal to 0 and solve it. So at x equals 2/3, my f of x, which is going to be 1 over 3x minus 2, goes to infinity. 1 over 0, which is infinity. So this is an improper integral. Okay, in addition to the other problems we have. So let's take a look at another example. And if you remember right, this 2/3 is on the interval that we're integrating, which is 0 to 1. So that makes this improper. Number one, we've got where it goes to infinity, and the point we have is on our area of integration. Let's deal with another one here then. Integral from 0 to 1 of 2x minus 5 over x squared minus 5x plus 6 dx. And again, you'd be tempted, this is a nice little u sub, okay, where my u is going to be x squared minus 5x plus 6. Du is 2x minus 5. So again, I've got du over u, which is going to make it kind of nice, except that we need to worry about when this is 0. So we take the denominator, so it equals 0. This factors nicely, x minus 3, x minus 2. And I'm going to have discontinuities then when x equals to 2 and x equals to 3. However, we're integrating from 0 to 1, so this is not an improper fraction. An improper integral, excuse me. Because discontinuities are outside bounds of integration. Okay, so there we go. So yes, we do have discontinuities, but because they're not inside our bounds, this is a proper integral, and you can go ahead and evaluate it. Okay, and I'm not actually going to do that. I basically showed you how to do it. So you end up with the du over u, and you've got a natural log situation. Okay, now improper integrals also exist. If one of the bounds of integration is plus or minus infinity. And let's take a look at a couple of examples of this. So first off, let's deal with the integral from a to infinity of f of x dx. This is improper. As is the integral from negative infinity to a of f of x dx. These are both improper. Now, one of the things we're always worried about is what's called convergence. Do these things actually converge on a value, in which case we could go ahead and actually find the integral, even with infinity. So convergence. So the limit as b goes to infinity of the integral from a to b. And you see what I've done is I've substituted b in for my infinity. Integral from a to b of f of x dx if this exists and is finite, in other words, you get a number, then the integral converges, and we can evaluate. Now let's come back over to this guy. So here what I'm going to do is, let's change this to b. So I want the limit as a goes to negative infinity of the integral from a to b of f of x dx. And this will diverge if the limit a doesn't exist. In other words, it's different from both directions, or b is infinite. And in that case, it diverges, and we cannot evaluate, at least using the calculus techniques that we've developed so far. There are other ways of handling it, but they're sort of beyond the scope of this course. As a matter of fact, it's graduate level math. Okay, so let's work a couple of examples. We've got the integral from 0 to 4 of 1 over the square root of x dx. So the question is this proper or improper? Problem is, this is improper because 1 over the square root of 0 is infinity. So the next thing we need to do then is figure out if this thing exists. We're going to take a limit as a goes to 0 of the integral from a to 4 of dx. I'm going to go ahead and rewrite this thing as x to the negative 1/2 dx. Okay, and so now we come back in, and we're actually going to evaluate this integral now. So that's going to give me, I add 1, that's going to give me 1/2. So this is going to give me the limit as a goes to 0 of 2 times the square root of x, evaluated from a to 4, to give me then the limit as a goes to 0 of 2 times the square root of a. Whoop, got it backwards. I'm going to have a limit as a goes to 0 of 2 times the square root of 4, which is 4, minus, because there's no a in here, the limit as a goes to 0 of 2 times the square root of a, which is 2 times the square root of 0, which is 0. So my limit, or actually my integral, is going to equal to 4. So this thing converges, because I have a finite limit, and you've actually already evaluated what it is too by getting this. Okay, let's work another couple of examples here. Well, the integral from 0 to 2 of dx over x minus 1 squared. Again, you'd be tempted to go ahead and just use up this. However, we need to find out where that is, and x equals 1, I have a discontinuity, so this is improper. because we have the discontinuity and infinite discontinuity at x equals 1, which is within our bounds. Now this is problem number 7. So look at, they've got a graph of problem number 7 on page 585. And you notice that this thing is symmetric about x equals 1. So what I'm going to do then is I'm going to break this up into 2 times the integral from 0 to 1 of dx over x minus 1 squared. And this is my problem child right here. So what I'm going to do then is take the limit as b goes to 1, and it's 2 times that, of the integral from 0 to b of dx over x minus 1 squared, which is going to equal to x minus 1 to the negative 2 dx. And this is a u sub. U is going to equal to x minus 1. du is dx. So essentially what I'm integrating here is going to be the integral from 0 to b of u to the negative 2 du. You add 1, so it's going to be negative 1 over u, which is going to be a negative 1 over x minus 1. So be evaluated at 0 to 1. And as you can see, I'm still going to have a problem because I'm going to have 1 minus 1, which is infinite. So this thing diverges. And at this point, we're ready to stop. Okay, so the last one then. Integral from 0 to infinity of e to the negative x dx. And again, my problem is this guy. So I'm going to have the limit as b goes to infinity, and I picked b because it's the top one, of the integral from 0 to b of e to the negative x dx. Okay, this is a u sub. I've got the limit as b goes to infinity. When I integrate this, I'm going to end up with the negative e to the negative x, evaluated from 0 to b. I'm taking the limit of a negative, which is going to be the limit b goes to infinity of negative e to the negative b plus e to the negative 0. So e to the negative b, or the limit as that is 0. So I've got 0 plus 1, which is 1. So this thing converges. And our integral is 1. And if you're wondering why, if you remember, e to the negative x looks like this. So as x gets very big, as x goes to infinity, my function goes to 0. Okay, so there are your examples. Improper integrals. Can show up in several places. First one, when you have an infinite discontinuity. And these usually are rationals. Not always, but they're usually rationals where the denominator equals 0. And the second place you're going to get them is when you have either plus or minus infinity as the bounds of integration. So you always have to worry about whether you have improper or not. Once you find out that you have an improper, all right, so we know we've got an improper. So the next thing then is to find whether or not it converges. To do that, you take the limit as x goes to whatever the value you have a problem is, of the limit of and if the limit is finite, then the integral converges. If the limit either A doesn't exist, which means it's different as you go from it from a negative to a positive difference, or B, it's infinite. Then the integral diverges and cannot be evaluated, at least by the methods we have shown now. So this is what we're going to be working on, our improper integrals. Remember, we're worried about where we have either, they always involve infinity in some form, either where your function goes to infinity or where your bounds is infinity.